Um, we're now recording. Just to let everybody know that. So this is going to be a talk about vaccines and the kinds of COVID vaccines that we have now, and the kinds of the differences and similarities that they have amongst themselves, and also some of the differences between some of the vaccines that we've used historically. So a little bit of, hmm, I think we should be able to see here. Might try headphones if that can't come through. If you're calling in, you'll make sure you need to join audio. So let's talk about vaccines. The structure of this talk is going to be a little bit about who I am. I'm going to introduce myself so that you know what I'm saying is real stuff. Then we're going to talk about how our immune system works, a little bit of anatomy and physiology. If it's been a while since you've had anatomy and physiology, that's okay. We're not going to overwhelm you. And then we're going to talk about how these vaccines that we're using now are different to some of the vaccines that we used historically. And then we're going to talk a little bit about what's next in terms of vaccines. I have a couple slides pulled up in case people want particular expansion on a couple question points, and we'll take some questions. So I'm guessing this will probably be like a 40-minute talk, give or take. So we'll see how it goes. All right, who am I? Like I said, I'm Dr. Callan Yoke. I am 4 years in now to being an Otterbein professor. I'm a disease ecologist. I mostly work on rabies and a couple other viral vectors, mostly to do with zoonotic infections. So not too dissimilar from something that we are dealing with currently, except I don't work with anything that's jumping in pandemic form into people. I have a PhD in evolution ecology and organismal biology. The organismal biology and ecology side of things is really my specialty. So that's the kind of stuff that I've done. I teach anatomy and physiology here at Otterbein, together with Dr. Sheridan and Dr. Marr. And so that's where my background in for a lot of this anatomy. And this is why I'm particularly interested in the immune system and the way the immune system functions in relation to a lot of these vaccines. I've done some bear work and I do a lot of dog stuff internationally. So that's why this is just who I am. Okay, so a little bit on the background about how vaccines and how our immune system functions. If you were to get exposed to a pathogen, COVID-19, influenza, herpes virus, anything that we're talking about, most of that's never going to get anywhere close to you. Most of the time, the either barriers in our skin, the mucous membranes in our eyes and in our mouth, there's systems already there to wipe out those defenses or wipe out those attackers before it ever starts infecting cells. So I very well may have been exposed to COVID-19, but there's a chance that my innate defenses crushed it before it was able to actually infect me. That's why not every single person that comes in contact with a infectious person and receives infectious particles is actually going to get sick. That's one of the reasons why that happens. So those are going to be your innate defenses. It's going to be things like the cells that eat other cells, natural killer cells, the inflammatory process. These are all things that it doesn't matter how often you've seen that pathogen, whether it's the first time you've seen it or whether it's the 20th time you've seen it, the innate defenses work pretty much as well as they are on anything. The adaptive defenses are really the star of the show when we're talking about vaccines. And the adaptive defenses are going to be the things that if you've seen it once, the next time you see it, you're going to be even better at fighting it. The third time, you're going to be really good at fighting that, right? The more you get exposed to a pathogen, the faster your immune response is going to engage, and the faster you're going to crush that potential infection so that you maybe not even aware that you ever got sick. And the stars of the adaptive defense mechanisms are going to be B cells and T cells. So we're not going to get into too much of the cellular side of things for the most part, but the two things that you need to know, need to be kind of familiar with are B cells and T cells. And we'll talk about what they do as we go. Sorry, I've been teaching all day. My throat's a little sore. So when we're talking about the immune system, what the immune system is actually looking for is it's looking for an antigen. Particularly, an antigen is some protein or a chunk of a protein, some unique sugar or something like that that is on the surface of a bacteria. So this rod-shaped bacterium that we have here has certain shapes on its outside surface. And those are going to be unique to that particular pathogen. So that these are oftentimes antigens are a protein that's on the surface of a pathogen that it uses to get into another cell, or some structure that it uses to attack other cells. So there's a reason why these things are sticking out and like covering the surface of a pathogen, but that's also what we use to identify them. That's what we, in the picture that you can see here, there's antibodies that have already been generated to go out and attack this thing. And these antibodies are binding to the surface of these antigens. They're binding onto that because of that very unique structure. And this is what enables us to attack a particular thing and not just like destroy a lot of cells indiscriminately. And the reason why we have this is the reason why we care about antigens is that there's a class of cells called antigen presenting cells, or professional antigen presenting cells if we're getting technical. And that's going to be a couple other cells, but the best one at antigen presentation is called a dendritic cell. Dendritic cells, when you have inflammation and when you have a pathogen starting to spread in some local area of your body, a dendritic cell comes along and eats chunks of those pathogens, or eats the pathogen whole if it can. Then that dendritic cell is going to show on the outside surface of that dendritic cell in what's called MHC1 molecule, but it serves on this little plate that says, hey, I just ate this thing. I just destroyed this thing. There's a chance that this is pathogenic, that this is causing disease. So when we are displaying this to the outside world, this dendritic cell can then go along to your other parts of your immune system, those adaptive B and T cells, and say, hey, can you bind to this thing, to this antigen? And if you can, you should be activated and you should go out and start looking for that because, hey, we're sick. We're getting infected by this thing, this antigen. So it's kind of serving as almost like a wanted poster, letting our B and T cells know what's a threat out there in the environment, out there in the environment of our body. If there are any questions along the way, feel free to jump in. It's probably far enough in that I'll turn on the ability to unmute yourself, but you can raise your hand and I'll pause and let you jump in and ask questions as you need to. So the B and T cells that we're talking about, particularly the T cell that I care about most in this presentation is called a T cytotoxic cell, or a killer T. This is a cell that goes out and kills other infected cells. So when we're talking about a virus will enter into our cells and then is basically hiding inside of our cells and using our cells as a place to generate new virion. Well, a cytotoxic T cell comes in and blows up that infected cell, killing the cell in the process, but also killing and damaging the ability for that virus to replicate. A B cell, when you display a chunk of that pathogen to a B cell, the B cell doesn't go out there and directly start causing damage to that virus. Where T cells go out and they're on the front lines and they're attacking and killing infected cells, B cells hang back, and then B cells will change into what's called a plasma cell. So a B cell becomes a plasma cell, and when it becomes a plasma cell, they basically turn into a factory for antibodies. They're going to go out there and generate antibodies. Those antibodies are just proteins that have a specific shape on the surface of the antibody that's binding with this particular antigen of whatever pathogen that they've been targeted to destroy. So when these antibodies are floating around out there, those antibodies are going to bind to that pathogen, and they're going to aid our ability to destroy it, either by what's called opsonization, making it more visible. So it's basically like tagging a pathogen with a little fluorescent flag that says, hey, this is something that we should kill. Or they'll just get in the way and they'll prevent that pathogen from actually binding with our cells. That's called neutralization. But antibodies are helping us by attaching themselves to that pathogen. So they're not actually normally directly killing that pathogen, but they're kind of aiding our ability to target it and aiding our ability to interrupt that pathogen's normal processes. So when we're talking about vaccines, in simple terms, all a vaccine is us showing our adaptive immune system, those B and T cells, something that is a pathogen, either one that is a chunk of a pathogen, so has zero ability to cause harm, like what we're going to be talking about today with mRNA and viral vector vaccines, or things like that stuff that you've probably had your whole life, the kinds of vaccines like the flu vaccine that are either what's called weakened or attenuated vaccines or killed vaccine. So when they show you that piece of a pathogen, your immune system recognizes it as foreign and recognizes that, hey, the next time we see this, we need to ramp up more quickly and to start attacking and destroying that. So before we talk too much about the vaccines that we're using in response to attack coronavirus, let's talk about how coronaviruses actually are causing harm to us. This is not so dissimilar to how normal viruses work. The only difference between coronavirus is that they're actually not inserting any genetic material into our nucleus. They're just inserting it into our cytosol. If you don't know what that means, it doesn't matter. That's okay. It's not going to influence it too much in your understanding here. So what a virus is doing is a virus, in very simple terms, is a little bit of genetic material in the center, either RNA or DNA. So deoxyribonucleic acid or ribonucleic acid. It's just a set of instructions. That's all that genetic material is. And it's a set of instructions to produce more copies of itself, a kind of cookbook on how to make more virus. And that genetic material is wrapped in a shell of some sort. Different viruses have different kinds of shells, but it's basically, that's it. It's not too complicated when we're talking about viruses. And the problem with this system is a virus, if you have a bacterium, that bacteria eats a little bit of sugar and then it splits into two. So now you have two bacteria. Well, viruses can't intake energy. Viruses can't reproduce. They have no ability to duplicate themselves on their own. So what they do is they hijack our cell. And it looks a little bit like something like this, where you have a coronavirus with these characteristic spikes. So we're going to come back to these spike proteins quite often. When you have this spike protein attached to the outside of our cell, it inserts a little bit of genetic material and it inserts it into our cytosol. It inserts some viral RNA. And that viral RNA is then going to be picked up by the ribosomes in our cytosol, in our cell just floating around. And the RNA is an instruction to make a protein. So what do our ribosomes do when they find this viral RNA? They start making viral proteins. So our cells make these viral proteins in order to, because they received this list of instructions. So when we make enough of these proteins, these viruses will actually self-assemble. And then now all of a sudden you have a new virus. And that virus will either reproduce inside that cell. Oftentimes it will kill that cell and rupture. And then now you have millions and millions of viruses that are now released where one virus had inserted DNA previously. This is one of the reasons why they're really easy. The viruses are particularly easy to spread. So the vaccines that we have on deck, there's a bunch of vaccines internationally. These are all the ones that are actually kind of currently in use. It's changing every day. I had to update this lecture 2 days ago because stuff changes. So this is a rapidly changing system, but the stuff that we have to deal with in the US is pretty much the big three: the Moderna, Pfizer-BioNTech, and the Johnson & Johnson vaccine. The Moderna vaccine was the first one. The Pfizer-BioNTech was the second one that came online. And just recently, we had the Johnson & Johnson, which is actually using a different little bit of technology to get us exposed to that portion of the viral antigen. Internationally, there's a couple that are in use. China's Sinovac vaccine, and in Europe, and actually elsewhere in the entire world, the AstraZeneca vaccine is far and away the most important vaccine internationally. It's the one being used most in Europe, Africa, South America, pretty much everywhere else other than the world, other than China and the US. AstraZeneca is the main vaccine, which is going to cause some problems later on when we talk about what's going on with AstraZeneca. Now, all of these coronaviruses vaccines, all of these different new ones that we're talking about, they differ from the kinds of vaccines that we've used historically. So here we have Jonas Salk, right? He's the one that made the first polio vaccine. This is a kid that's getting a little bit of oral polio. We've been doing dead or weakened strains of pathogens and exposing our immune system to them for a long time, right? This is the way that we built vaccines initially. And historically, even still today, most of the vaccines that I've received are inactivated or attenuated vaccines. Or inactivated and killed. So this is not particularly new stuff, so we don't really need to talk too much about this, but this is the way things like your normal seasonal flu, rabies shots, the kind of standard vaccines, they're showing your immune system a broken up piece of some pathogen, and then you start eliciting an immune response to that foreign antigen. But the new stuff starts to be a little bit different. Subunit vaccines are about 15 years ago, subunit vaccines started to come onto the market. You've probably heard of Gardasil. Gardasil is probably the most common subunit vaccine. It's a protein vaccine where they're not actually showing chunks of the pathogen, but what they're doing is they're just displaying a particular protein. So they're showing you a bunch of viral protein, but there's no RNA or DNA, or there's no ability for that little chunk of protein to make new copies of itself. It's basically showing the shell of a virus. Like I said, HPV, human papillomavirus, we use Gardasil against quite commonly. It's starting to be part of like the normal suite of vaccines that you receive in childhood. Novavax is one that's potentially going to be used against COVID, but it's still moving through trials. So we're not super sure where that's going to end up yet. The new stuff that we need to be concerned about and understand is mRNA vaccines. mRNA vaccines are not entirely new. We've been using mRNA vaccines for a while and testing mRNA vaccines, but there hasn't really been as big of a need for mRNA vaccines because we've already had other vaccines already on deck to use against other pathogens. So we've been kind of slow to produce things like there's a cytomegalovirus CMV mRNA vaccine that we've been working on for 15 years. There's a rabies mRNA vaccine that we've been working on for 20 years, right? So this is not new stuff. It's just there hasn't really been a reason to replace the sorts of vaccines that we already have against those pathogens. What mRNA vaccines do is an mRNA vaccine is presenting an antigen, just like any other vaccine does, except the antigen is being displayed and it's actually being produced by our own body in an mRNA vaccine. When we're talking about COVID-19, most of the vaccines that you're going to see come to market and be used out either in the US or internationally, most of them are going to be operating on this. It gives this characteristic name for the coronavirus. Corona means crown. So it almost looks like a little radiant halo around when you look at this under a microscope. So this is the crown of a coronavirus. And it's this spike protein, the S protein that we see here. We have, since very, very early on in the pandemic, before it was actually a pandemic, we've known exactly what the spike protein looked like. Very early on, China was actually very good at getting out sequencing DNA or sequencing information to display this sort of picture that you see right here. This picture is exactly what that spike protein in a virus looks like. So the spike protein is targeted because it's the most visible. It's the easiest thing for our immune system to see, rather than some kinds of proteins that are within the shell, or things that are just less visible, less accessible to the outside. So what is mRNA before we take a step into mRNA vaccines? When you are generating a new protein in your cells, this is happening billions of times an hour in your body, so this is not a rare thing or anything. When you're generating a new protein because a protein is broken or you need a cell to divide, so you need more proteins before that cell splits in half, you generate RNA. And what RNA does is RNA actually takes this genetic material, the DNA, this like permanent cookbook. And what it does is it brings that information, it's takes that genetic material out into the cytosol of the cell, out where it can interact with the ribosome, and then that ribosome transcribes it. So the way that I kind of think about this is like this is a book in the library, right? So the DNA is a book that's in the library that you're not allowed to take out of the library. It has to stay there. It's one of the fancy encyclopedias or something, right? If encyclopedias still exist. Maybe they don't anymore. So this book that has to stay in the library, you take a little copy of it, right? You make a copy of that, and it's a photocopy, but it's a pretty good photocopy. It's almost an exact duplicate. And then when you take this home, now then you can, if this is like a recipe, then you can actually cook this and make that product. In this case, the protein is that end product. So that's what RNA is doing for us. Our cells are using RNA to generate proteins. That's a normal process. When we're talking about the RNA vaccines, they're using this system where we have our genetic material being expressed as RNA, and then that RNA being translated into a protein. Well, the Pfizer-BioNTech and the Moderna shots are mRNA vaccines. Well, what does that mean? Well, instead of the sorts of old technologies where if this were a killed vaccine, well, I would basically heat up some coronavirus, kill it all, and then I'd shove those chunks of dead virus into you. And then you'd elicit an immune response against it. And then the next time you saw live virus, you would be able to protect yourself against that pathogen. Well, the Pfizer-BioNTech mechanism does not, and Pfizer-BioNTech and the Moderna shots don't expose you to any foreign pathogens. There's no foreign pathogen or foreign pathogen proteins even. What they do is they actually, the contents of the Moderna shot is mRNA, just like it sounds. And what they're doing is they're delivering this mRNA packet inside a little fatty shell, and your cells uptake this RNA and they say, hey, what's this RNA? These are instructions on how to make a protein. Let's make this protein. Almost like a pathogen would, right? If we have the coronavirus attaches it to a cell, it inserts RNA, but it inserts RNA for the instructions to make the entire virus. The Pfizer and BioNTech and Moderna shots, they only insert the instructions to make that spike protein. And that's a big difference. Obviously, a spike protein is not genetic material. It's not able to replicate or self-assemble or anything like that. So what these spike proteins do, now that we've generated a bunch of spike protein in our cell, well, some of them are going to move to the surface and embed inside the surface, and they're going to look like part of this cell. And some of them are going to be displayed on a product called an MHC1. MHC1 is the window into the cell to let cell know, hey, this is something that I'm making inside me. This is a window into letting the cell, other cells that are coming by, know that this is something that's being produced. Well, when this happens, when you produce spike protein and display it on the outside surface, what's going to happen is your cytotoxic T cell or your killer T cells are going to come along and they're going to bind with that spike antigen that's being displayed on that MHC1, that plate to say, hey, this is something that we should be concerned about. This is something that I'm making. And when that happens, the cytotoxic T cell says, hey, you're not supposed to make spike protein. If you're making spike protein, you're infected by a viral cell. So what is that? What does this cytotoxic T cell does? It kills it. It kills that cell that has uptook portions of that mRNA. Well, now you have just a bunch of inflammation, right? Because this is cells dying is not a fun thing. It's going to eject all of their contents, and the contents are going to cause an inflammatory cascade. You're going to get redness and soreness and a little bit of injection site pain, right? You're going to have a little bit of cellular death. Any cell that uptakes that viral mRNA is going to be attacked and destroyed. The good reason for this, the reason why we want a lot of inflammation, when we want an area to feel sore and red, is because that means the inflammatory process is happening. And when we have we have tissue becoming inflamed, that's going to recruit other immune cells. So it's going to recruit T cells and other neutrophils and other cells that are going to attack and destroy pathogen. as well as it's going to recruit more dendritic cells. The more dendritic cells that are recruited to an area and that phagocytose that eat a little tiny chunk of that antigen, the more spike protein that we're going to display to our immune system. So if this is your first shot, you're probably not going to get a big response. But the second time, now you've already primed a few of your immune cells to go out and look for this pathogen, which is why the Moderna shot especially has kind of, it's a little bit rougher the second time. You'll be not feeling great. You'll feel fatigued and you'll feel inflamed and there'll be some injection site pain. But we very much, that is a useful process because that means that there's inflammation going on. The more inflammation, the more dendritic cells that are being recruited, the more these dendritic cells are going to B and T cells, and the greater number of B and T cells that are being displayed this viral antigen, the more of them that are going to be ready the next time you might get exposed to wild coronavirus. Coronavirus that's out there in the environment, that is somebody sneezed on you and then now you have an exposure event. So the immune system needs that inflammatory process. We want inflammation, at least a little bit, in order to do this. So now, at this point, these dendritic cells are showing this spike protein to our B and T cells, and now our B and T cells are going to go out there and look for that spike protein. And if they've come across it, they're going to destroy it. They're attaching antibodies to it. This is a nice system because there's no viral DNA, right? This is not like an oral polio shot or attenuated influenza or anything like that. There's no ability for you to become infected by a coronavirus mRNA vaccine. You can't get sick from this. The crumminess you may feel afterwards is purely the inflammation. So much so that when you have that, we had that image of like all of the proteins coming together and forming a new virus. Not only do you not have viral DNA to code for those, but you don't make those other proteins. There's about 29 proteins inside a coronavirus vaccine or coronavirus that the vaccine doesn't code 28 of them. So there's no way that you could have anything other than just spike protein being generated. This is one of the really good benefits of an mRNA vaccine. One of the problem is mRNA is, or any genetic material, especially mRNA, is really fragile. Anybody that does genetic work is very well aware of how fragile the RNA is, which is why we need fancy -80 freezers to freeze that RNA so that it doesn't heat up a little bit and break down. If it breaks down, then it's not going to code for that spike protein and you're not going to elicit an immune response. This has made this a little bit complicated, which is why the rollout has been pretty slow initially. We've started to kind of get the kinks out of things as we move along. And it's also why like waiting lists exist, where if you start cooling vaccine, or if you start warming vaccine up to give to somebody, as soon as you take it out of the freezer, a clock starts. And if that time runs out on that clock, that vaccine can't be used anymore, which is why waiting lists where somebody misses their appointment, their car breaks down, they forget about it. I don't know how you could forget about it, but if you miss your appointment, somebody else will be able to jump in and take that shot before it goes bad, right? Get here in 15 minutes to get your vaccine type lists. When Kendall is asking a question, when you hear about people having adverse reactions, do you know any internal possible reasons for why this can happen? Is that part of inflammation reaction? Yeah, so adverse reactions are beyond the expected level. So adverse reactions are going to be things like, you're going to include stuff like a really bad fever as part of that, right? You want fever. You don't want too much fever because then you're just really uncomfortable. You're not going to generally have so high a fever after a vaccine that you're actually even really going to be in any danger, right? Like 102 fever feels terrible, but 102 fever is not any threat to a otherwise healthy adult, right? So that is part of the inflammatory cascade. We want some of those to happen. It's just occasionally some people have genetic differences between them, right? So that is the mRNA vaccines. The Pfizer-BioNTech and the Moderna vaccine. The viral vector vaccines, the only one that we have on the market in the US is the Johnson & Johnson vaccine. And this is going to be operating on a pretty similar structure. And the difference between this is instead of giving you a little bit of RNA that's wrapped in a little fatty coat, what the Johnson & Johnson vaccine is doing is it's also showing you spike protein RNA, the same sequence of RNA that shows you how to produce this spike protein, except we have taken an adenovirus. So adenoviruses are really common in people. It's what most of common colds, a lot of them are adenoviruses. It's going to give you flu-like, cough-like symptoms. But in this case, we've actually taken a chimpanzee adenovirus. And we've taken that chimpanzee adenovirus. Remember, a virus is genetic material to create more of those viruses wrapped in the proteins that they cause to be generated. Well, in a Johnson & Johnson vaccine, they take this adenovirus shell and then they basically scoop out all of the chimpanzee adenovirus. There's no chimpanzee adenovirus left. They just have the shells remaining. And then you fill that shell with that coronavirus spike protein RNA. So when that happens, you're going to give this person a shot. It's going to contain chimpanzee adenovirus that has the no chimpanzee adenovirus DNA or RNA, but it has that spike protein RNA. So then you give it to a person, it's going to invade their cells. Does anybody have an idea why you would use a chimpanzee adenovirus? If human adenoviruses are very common, and we've all been exposed to tons and tons of human adenoviruses, why would you want to use a chimpanzee adenovirus? Any idea? They're pretty genetically similar. So that's why we wouldn't want to use something like, I don't know, whale adenoviruses probably exist. So using a chimpanzee adenovirus means that virus probably can get into our cells reasonably well. That's a good start. And I think Justina and Laura are on the same page. We already have, if I have 3 young kids, I have been exposed to every human adenovirus that I think is probably on the planet. I already have antibodies and T cell responses to most of the human adenoviruses. If I were to be exposed to maybe a altered version of this Johnson & Johnson vaccine that instead of using a chimp adenovirus actually used a human adenovirus and scooped out the contents, I would have an immune response against that, and I would probably kill that virus before it came anywhere close to my cells. So I wouldn't really have the ability to get exposed to that coronavirus spike protein. That's why we use something that's similar, but not quite the same. It's kind of an odd thing to use a chimp vaccine or chimp adenovirus, but it's for a very, very good reason. So at this point, right, a viral vector vaccine is pretty much operating at the same way that an mRNA vaccine is operating. The benefit of the Johnson & Johnson is you tend to have a pretty profound immune response the first time, so you don't need more than one shot. The Johnson & Johnson is a one shot and done vaccine, whereas the Moderna and Pfizer-BioNTech, you generally don't have that much of a response. You don't have that much of an inflammatory response for that first one. So you actually don't end up getting enough antigen presentation to provide adequate protection. So that's, at this point though, the Johnson & Johnson's the same, right? There's no difference between this. You get a Johnson & Johnson vaccine, it makes spike RNA, that spike RNA gets displayed on the outside surface, and then things happen in the exact same sort of way, right? The T cells come along, dendritic cells come along, scoop up that antigen. So the side effects that we were talking about, nobody wants to feel bad after a vaccine, right? But we really should consider these as good responses. We want an inflammatory response. Inflammation, I don't feel good when I have joint pain or when I have a headache, but I feel that way because I'm inflamed, because my immune system is ramping up to fight a pathogen. It just so happens that this pathogen isn't actually going to cause me any harm because it's just a bunch of spike protein. But I'm producing a robust immune response I'm recruiting tons of B cells, tons of T cytotoxic and T helper cells to go out and fight spike protein. And then the next time I get exposed to it, I'm going to have a ton of soldiers on my side of the war ready to immediately quash this. This is a graph that shows you the kinds of things that you'll be seeing. The black line shows like placebo. So in the Moderna vaccine, about 70% of people that get in the second dose tend to be relatively fatigued. That fatigue just means they kind of feel tired. Well, 25% of people, right? I feel fatigued on most days, right? So the placebo still has about a quarter of people feeling fatigued. And then when we're talking about like things like vomiting, that's obviously a little bit more of an excessive response. Muscle pain and joint pain are lower, but they still show up. Haley asked a question, would inflammation cause blood glucose levels to increase? I had my vaccine already, and I noticed a spike in my levels for a couple days afterwards. Oh, I assume you're diabetic and you're monitoring as you go. The inflammatory response would, yes, it could alter that, mostly based on, it would influence like insulin and glucagon, but it could change that. It shouldn't change it too substantially. But if it's pushing like your blood glucose into like dangerous levels, then that's something that you should probably talk to a doctor about. A different kind of doctor, not a disease ecologist. Go talk to Dr. Marr. So what kinds of vaccines should you get? I'm not sure I can be any more clear about my feelings about the sort of vaccine that you should receive. Of the things on the market right now, the Moderna, Pfizer, BioNTech, and the Johnson & Johnson, I would have no qualms whatsoever taking any of them. I've not been offered because I'm not in the age class or risk category yet, but I'm patiently waiting and anxiously waiting my turn. As when they begin to be offered for my children, I'm going to have all three of them. Once they pass phase 3 trials, that is not concerning to me at all. And that just to show you the level of trust I have in the system that's generated these vaccines. There are some problems though. And this is something that I'm kind of anticipating somebody to have a question about, where when the Pfizer and BioNTech came out, the Moderna shot came out and said, hey, it's a 94%. And then the Pfizer came out, I think a week and a half later, and they said, we have 95% efficacy against symptomatic infection, which is great. Those are great numbers. If someone is not symptomatic, they are much less likely to spread pathogen. They're not 0% spread, but certainly if you are able to reduce the spread by anywhere close to 90%, this makes a real dent in our ability, or in the ability for this virus to spread. When the Johnson & Johnson vaccine came out, it wasn't discussed with the nuance that I think it required in most parts of media that I'm at least exposed to and consume. It really had, because when the Johnson & Johnson came out, it says, oh, it's 72. And obviously people seemed disappointed that that vaccine was not as effective. A 72% efficacy vaccine is still really, really, really good, but there's a couple issues to do with having a chart like this that just directly compares these numbers. One additional thing that often gets left out of the discussion when we're talking about between these vaccines is all of them have 100% efficacy on reducing hospitalization and death, right? So a 72% reduction in the appearance of symptoms is nice, but 100% reduction in the appearance of death is even better, right? So that's not necessarily a bad thing. It's not a inherently worse vaccine. Additionally, it's not really comparing apples to apples. This is really like an apples and oranges, right? Not only is that reduction in death a huge deal, but the Johnson & Johnson study was done after Johnson & Johnson entered and left phase 3 trials after the Moderna and after the Pfizer BioNTech had already finished theirs. Got a slightly hot mic. So when you are talking about, hey, this efficacy was 72%, well, the reason for that is that was already at the time that we had things like the English variant and the South African variant circulating. And those are different enough that they're probably going to mean that the vaccines that we have now are a little less effective against them, but they're still somewhat effective. When you saw numbers like 65 and 50% coming out, those were coming from, for the Johnson & Johnson, those were coming out of South Africa and Brazil, where their phase 3 trials were running. And those are places that there was a ton of variants widely circulating. So that's explains some of this difference in efficacy, right? It's, if you had run the Moderna and Johnson and Pfizer BioNTech trials at this time where the Johnson & Johnson was, I would probably expect similar efficacy numbers. So the reason why they're much higher is because there wasn't these variants circulating. So this is one additional reason why we need to get everybody vaccinated now to cut off these variants from becoming too established. So how are we doing on vaccine? We're doing pretty good. Overall, the US is doing pretty good. What you can't see at the top here, the darker the shade is the higher doses administered per 100 people. So we are approaching the 30% range. So we're getting pretty close. Ohio is kind of middle of the pack for a lot of states. I'm not ecstatic with Ohio's rollout. I'm not angry with Ohio's rollout. I'm kind of okay. There's other states that have a lower population, places like North Dakota and South Dakota and Oklahoma. They have a lower density, so it's a little bit different scheme. But we're doing okay at rolling out vaccine. About 12% as of yesterday, these are yesterday's numbers, are currently fully vaccinated, either receiving one of the Johnson & Johnson or two of the 2 mRNA vaccines. So this is not bad overall. And if we continue along at about this current rate of immunization, we're probably actually going to be slightly faster, because now the Johnson & Johnson vaccine should take us up at a higher change. We're looking at about 70% of people being vaccinated by the end of June. Estimates on how many people do you need to have herd immunity, you can go and watch epidemiologists argue about this. We don't know what it is. We won't know until we already hit it. But the best estimates are somewhere around a 70% should bring the spread low enough that it's not going to be spreading wildly in the community. So if the Johnson & Johnson rollout goes better, right, we will have a higher pace. So there's a chance that we could be hitting those sorts of numbers earlier, but we will wait to see, because I can't predict the future just as much as anybody else can. And now I have a couple slides that are just kind of responses to questions if people have them, or anything. I can go through those extra slides. Kendall has a question. If you caught COVID and your body has built up antibodies naturally, is that not enough? So it probably is, but there's a chance that it's not. So you should get the vaccine. There's very little cost to getting the vaccine. If you produce an immune response, depending on how your case went, your immune system could have been like under severe affront, and you might not have been able to produce an adequate response, depending on if you caught COVID and had a very light case, right? You probably didn't get that much antigen presentation. So something like a vaccine would be beneficial to kind of pump up your memory B and memory T cells, those cells that are remembering and waiting for that next exposure. Additionally, there's always a chance that you got a different variant when you became infected, and the spike protein has changed slightly, and maybe the spike protein from when you got it to when the spike protein for that Moderna shot, if you get that one, maybe they're slightly different in shape. So it's better to have two wanted posters than just one, right? The idea that if you have a slight change to the shape of that spike, you want to be able to nail that new spike protein as well, which is also why that you should expect in the next few months booster shots to roll out that have altered spike protein shapes. Should you still get the vaccine? I did finish. So I would still get the vaccine. Would one be considered better than the other for someone who is younger with no underlying autoimmune conditions? No difference whatsoever. A question that I was expecting. When we are giving someone a dead strain, the dead strains are completely destroyed. Someone that's immunocompromised, they have SCID, they have severe combined immunodeficiency syndromes or HIV, that kind of thing. The general rule is dead vaccine, they can take it, but weakened vaccine, you wouldn't want to give that to somebody immunocompromised because you might have issues with their immune system not being able to produce an adequate response. How long is it thought that the vaccine's protection will last? I cannot tell you. No one can tell you. There's no evidence that it varies between vaccines yet. Caitlin's question, a lot of people will focus on the antibody count, right? So when you start activating B cells, they're going to produce antibodies, right? And those antibodies are proteins. Proteins break all the time. That's not a weird thing that proteins break. So antibodies, you're going to have a spike, and then those antibodies are going to continue to be produced for a little while by those active B cells. But over time, your antibody count is going to go down, and it's okay. It's not a problem that it does. The B cell that makes them, those memory B cells, are not generating new antibodies, but they're still waiting around. And you still have T cells, like the cytotoxic T and the helper Ts. We didn't talk about helper Ts today, but the helper Ts are still there as well. It's really hard to measure how many cytotoxic T cells somebody has. So we use this ability to measure antibodies. And then a couple months ago, you saw a bunch of news articles saying like, oh, people's antibody counts are going down quickly. And okay, that doesn't tell you that they're going to lose immunity. Antibodies are not our only immune response in this. There's those memory B and T cells that are going to be able to activate quickly, as well as the still active T cells. So Bridget asks a question, do viral vaccines elicit a higher immune response compared to mRNA vaccines? That is the idea why we don't have to do 2 doses of a Johnson & Johnson. So the Johnson & Johnson viral vector vaccine, as well as the Sinovac is the Chinese viral vector one. Those are going to produce a higher immune response because it's a more effective entry into a cell rather than just the Johnson & Johnson and Moderna or the Moderna and Pfizer BioNTech, the mRNA vaccines. It's a little snippet of RNA and they wrap it inside this little fatty coating. Well, a lot of those aren't actually going to get into a cell because there's no like attachment mechanism. But when you compare that with like a chimpanzee adenovirus, that adenovirus, it sure knows how to get into cells. So that's why you're going to have a little bit more exposure from a single shot Johnson & Johnson compared to the first shot of either the mRNA. Janie asked a question, since the Pfizer and Moderna are based off mRNA, do you think those are any risks in younger individuals, such as infertility? There's absolutely no evidence of infertility. mRNA does not change your genes. This is something people ask questions. When you take a Moderna mRNA vaccine, the mRNA is immediately uptook by your cells, and then immediately so basically you're skipping this step where you're like coding your genetic material into RNA. So basically the vaccine is they just give you this, and then your cells make that spike protein. there is no mechanism for RNA to go backwards into the DNA, right? That's not how RNA works. And remember, RNA needs to be kept at -80 to keep it shelf stable for a long period of time. My body's not -80. So this RNA is going to disappear pretty quickly, on the order of a couple days. I get a Moderna shot. A couple days later, there's 0 bits of that shot left in me. The only thing that is still inside me is those spike proteins that are being generated. Um, so there's certainly stuff that we don't know. But there's no reason to think that they would cause problems. And there's lots of reasons to think that coronavirus causes problems, between death, which is a big one, but even people that survive have pretty significant heart damage, pretty significant lung fibrosis, scarring. Um, Blood clots are becoming an issue because a lot of particulate matter comes out from this, and it ends up causing clots in places that you really don't want. So, like stroke and uh, getting clots thrown to your lungs is certainly an issue for becoming infected. The risks are virtually zero on the vaccine side of things, and well known on the other side. Um, so, like Cameron says, hesitancy is reasonable, right? There are lots of reasons to be hesitant, and there are reasons to be inquire and want to learn more. Um, when we're talking about hesitancy, it's important to distinguish that between somebody that's like an anti-vaxxer, right? An anti-vaxxer is not the same thing as somebody that's hesitant to take a vaccine. You are hesitant because you need more info, right? So it's important not to like compare them as if they're one and the same. And this is actually a good reason, a good argument for learning more and more talking more with people about the vaccine, because uh, when you look at, so this is an NPR Marist poll that just came out on like the kinds of people who feel the yellow is no, they would not take the vaccine. The dark green is yes, and the light green is I've already had it. So the kinds of people that would get the vaccine, the more information that we can provide, the more it pushes people towards a yes. So mRNA affect medications people take or lessen vaccines effectiveness. Not any sort of like medications that you would use to like manage blood pressure or like SSRIs or anything like that. But there are actually good reasons not to take like a leave. There's a comment from the CDC yesterday, I think, about how they don't want people to like take a leave, then go get their shot in like anticipation, because a leave is an anti-inflammatory, right? We don't want to tamp down the inflammatory response. We want to take anti-inflammatories, like non-steroidal anti-inflammatories like NSAIDs. We want to take those after we start to develop bad inflammatory responses. We don't want to kind of take them ahead of time, because that prevents antigen presentation. It prevents our dendritic cells from doing their job. Kendall, do you see this being mandatory for travel? Probably. In the same way that I can't go to Kenya if I don't have my yellow fever shot, or parts of Kenya. I can't. I could very easily see this being something that is, at least on a state level, enforced. You have to have meningitis vaccines to come to campus and like live in the dorms, right? Because turns out meningitis with a bunch of crowded young kids kills people if they don't have that. So it's already done for some things. And this is going to be, so Justina, for my anatomy and physiology class, this is going to be available to you later. One other thing I wanted to talk about is kind of a new thing. The last thing I wanted to mention is the idea, the news that's coming out of Europe with AstraZeneca currently. So this is like current stuff that this is why I had to like change this presentation very, very recently. The France, Germany, Poland, the Democratic Republic of the Congo, a couple other countries have actually stopped using, they've halted their use of AstraZeneca because there's been a report of people getting blood clots after they take the vaccine. And this is honestly pretty weird. This is a rapidly changing situation because maybe next week this is nothing, and maybe they've started up their AstraZeneca applications again. But this is not great as of right now. The kinds of discussions that are going on around this have been really poorly framed to the public because in just Europe alone, there's been 17 million AstraZeneca doses. AstraZeneca, again, is the one that's going to be given to pretty much the entire world other than the US. That AstraZeneca is very common internationally. And just in Europe, they've had 17 million doses, and a report that has caused all of this problem is the idea that 30 people have developed blood clots within a couple weeks of getting their shot. 17 million doses and 30 people, right? This has already gone through phase 1, phase 2, phase 3 trials, and blood clots were not something that were highlighted as a concern during those trials. Now, I'm not to say that a vaccine has never made it out and that needs to be changed, but 17 million doses to 30 doses is currently not in my opinion, in the European Medical Association's opinion, in the CDC's opinion, is currently not enough to reasonably stop vaccinating people against coronavirus for this. This is actually 30 per 17 million in the period of time that we're talking about is actually lower than the background rate of clots. So the evidence to right now that is publicly available would show that this AstraZeneca actually protects people from clots because blood clots happen all the time, irrespective of vaccines. Additionally, coronavirus is a blood clotting, has a tendency to cause blood clots in people. So right now, there is not publicly available knowledge that explains why this has happened. And it appears to be more a political decision than a scientific decision. So keep an eye out for trying to figure out what's going on with this. But this is currently kind of confusing why this has happened. And I think that was all the extra slides I had as well. Yeah, okay. That's all I have for everybody. We're about right around where time I was expecting. If there's any other questions, I can hang around for a little bit. Does it contain any stabilizers? So I don't know 100% the types of stabilizers, but it would contain stabilizers. Thimerosal got surrounded with the autism being caused by measles, mumps, and rubella vaccine. Thimerosal kind of got slandered in that thing. And then all of the stuff that blamed mercury for that issue with autism got retracted because it was actually made up data. But we still removed thimerosal, even though we found that thimerosal wasn't actually a problem. There's all sorts of stuff inside a vaccine that sounds very scary. There's formaldehyde in vaccines. Formaldehyde is useful at preventing like a bacterial infection from growing inside of a vaccine. Formaldehyde sounds like a scary thing because it's a scary chemical that you don't want. Well, the problem is dose is pretty important. Uh, the lethal dose, or the dose enough to cause disease with formaldehyde, is way higher than the amount of formaldehyde that's in all of your vaccines. If I were to take every childhood vaccine that is part of the normal suite of childhood vaccines, and you put all of the thimerosal that, or all of the formaldehyde that's in all of those vaccines, there's actually 8 times more in a pair sitting upstairs on my counter, right? And I don't have like some weird pair with that's formaldehyde heavy. Formaldehyde exists in our cells. Our cells make formaldehyde. Fruit makes formaldehyde. Formaldehyde is something that is produced in nature. The idea that there's formaldehyde in a vaccine, so it's dangerous, is disingenuous from people that are not necessarily good actors and aren't arguing in good faith. Janie asked a question: how soon do you think this vaccine will be implemented as part of a travel and opening back up? So Ohio just opened up, so that the end of next month, they are expecting, they're making it available to anybody over the age of 16. So pretty soon after that, I would imagine that I'm optimistic about a return to semi-normalcy. Mask usage will probably still continue, but that will be like one of the final things that we peel away from that's kind of blocking normal life. I after vaccination, I plan on going back to living a fairly normal life. So I think that this vaccine, I'm probably another 2-3 months. Bridget has a question. Just read an article on COVID infected immunocompromised and high mutation rates leading to a better virus. Is there precedence with other viral infections regarding closely monitoring or following these patients to prevent escape to the community? There's certainly evidence of long-term infection. That is actually really common in HIV. It's really common in herpes, like a lot of viruses that reside in the body for a long time. The COVID long-term, and people are called long haulers. They're people that are like, either they actively have virus, but generally they don't have virus, and they aren't infectious. They just are suffering with the effects for a long period of time. A virus will generally become more contagious as time moves on, and it will generally become less lethal, because being lethal is a bad strategy evolutionarily to a virus, but it's all random, right? Mutation's random. The general trend is towards more infectivity, but that's not necessarily always the case. You're not going to be able to monitor people because oftentimes if you're long-term infected, you might not know it. So it'll be hard to look at that. This is why sequencing data is really useful. So the US has done a pretty poor job of sequencing compared to some other countries. The reason why they found an English strain and they found a South African strain is because they're doing a large amount of sequencing. We aren't. So is there a Minnesota strain or a Westerville strain? Maybe, but we're not doing enough sequencing currently to know that's the case or know that it's not the case. That's why sequencing is kind of like turning the light on in the room. You might see a monster, or you might confirm that there's not a monster there, right? So sequencing is really important, and we're not doing enough of it right now, unfortunately. The more people that get infected, the more chance for a variant to occur. So which is why There's probably a lot of variants coming out of Brazil. There's probably a lot of variants coming out of South Africa and the US, but these are generally not variants that are going to be too concerning. Ivermectin is antibacterial, and it might have some benefit in the fact that ivermectin could interrupt the mechanism by which the coronavirus is actually insert a little protein that copies their DNA once it's already inside your cells. So it basically makes more copies of itself before you start producing its proteins. And there's the idea that ivermectin might interrupt that process, and that's unclear. Trials right now show that ivermectin is pretty much as good as a placebo. It is also an antibacterial, so it would stop you if you get like a really bad lung hit from coronavirus. Oftentimes, what then causes additional problems is then your lungs will be invaded by bacteria. And then if you already are on ivermectin, that could be a benefit, but it's unclear how effective it would be used against the virus itself. Like I said, best evidence right now is that it's about as good as a placebo at preventing people from moving to a ventilator or potentially dying. It's kind of the same argument around hydroxychloroquine, right? That became weirdly political as in terms of medical advice gets. Okay, well, I think thanks everybody. I'm gonna wrap it up here, and I'm gonna stop recording.